Hi, this is a lecture video for the chi-square statistic test for independence. In the last video, we saw the how to perform a test for goodness of fit. So this is the other kind of test that you can perform with the chi-square. So this test for independence is specifically testing for whether there's a relationship between two variables. So any given individual can be jointly classified along each variable and one of the categories of the variable. So the diagram here looks a little bit different. So we're looking at counts again, but you can see that we're now working with a matrix. So the way that we're looking, that we can see these sorts of matrices and understand them, is that we have a variable on one side along the rows with any given number of categories. Here we just have a variable with two categories, variable one, and we have another variable which we can see column-wise. And again, here we just have variable two with two categories for that variable. But it can be, again, any number of rows or columns. It's also important to make note of the row totals, what the frequency count is, how many people were in this particular row, and each row, however many rows there are, as well as columns. So column totals and row totals figure into our calculations, as well as whatever the sample size is, n. So you can find n by adding the row totals together or by adding the column totals together. So we'll see an example in a little bit, but let's talk a little bit about the null hypothesis for a test for independence. So the null hypothesis will state that the two variables are independent. That is, that there's no relationship between them, or you can't make any predictions about the other one based off of the first one. Um, the frequency distribution for one variable will have the same proportions for all of the categories of the other variable. So let's go into an example, and then we can go more into detail into the null hypothesis. This is example 15.3 from your book, and this is just summarized. So essentially, that example says that um, a woman and a man are told to discuss organic cookies. So that's the research setup. So they think that they're going to be discussing, the merits of organic versus non-organic cookies. But prior to this discussion, the woman was actually waiting in a room, and that room was either playing romantic music or it was playing neutral music. So that would be variable one, the type of music that was being played. And then after the discussion, the man who's actually part of the research team, a Confederate, uh, according to a script, asked the woman for her phone number. So the question that the researchers are trying to determine is whether the type of music, variable, the first variable, playing in the background, can help predict whether the woman is going to say yes or no to the man's request, right? So the second variable is her response to the request. So let's look at um, the null hypothesis again. So the null hypothesis again, is that the two variables are not connected to each other, right? They're not related. They're independent. Um, and so let's go into what this means, that the frequency distribution for one variable will have the same proportions for all categories of the other variable. So we can conceptually think of a test for independence in this way. So we can think about it as as if we were taking two different samples, a sample of women who listen to romantic music. So we can think about it like in this row, right? Like row wise. So we can have 100% of women in this particular sample, right? So it had a particular distribution. And we had another sample of women who listen to neutral music, right? So it would be as if we're comparing, as if these two rows are two different samples and we're comparing them. So um, to say that the variable type of music makes no difference is to say that they're not, that you're going to see the same distribution uh, for these two samples, right? So, for instance, if a woman within the romantic sample, music sample, if 60% of them actually were willing to give their phone number, and we saw that out of the neutral sample of women, also 60% of them were willing to give their number, then you can conclude that the type of music doesn't actually make any difference, right? So if the type of music made a difference, then we should see a difference if within these two samples, right? So um, when they're independent, when there's no relationship between them, they'll have the same proportions, distributions. So that's maybe a little bit counterintuitive, but when you think about it, it actually makes sense. If they actually are related, if, for instance, the type of music does have some bearing on whether they say yes or no, then you'll see that it would be different, right? So um, perhaps under the neutral music, only 30% of the women actually give their phone number because the type of music did make a difference. Um, so let's move on from this and actually talk about our frequencies, right? So similarly to the previous test that we looked at, the goodness for fit, we have observed frequencies and expected frequencies. So the observed frequencies, again, they're just what we observe from the actual sample. We take the sample and we get their information, or in this case, it would be a kind of a pseudo experiment, right? It's not a real experiment, but we're really just classifying people into these categories. That's how that's the justification for using the chi-square statistic, right? Um, so it's the same thing. So we have a sample, and here we could see that the sample was of 100. So if you add 50 and 50, that's 100, and similarly 42 and 58 is 100. So the distributions look like this, right? So that's actually what came out. Our expected frequencies, again, are going to be based on the null hypothesis of what should be expected if there's no relationship between the two variables. And similarly, we can to the goodness of fit test, we can use a formula to calculate what the expected frequencies would be in each of these little boxes. So our formula is that we have to take the totals, the frequency totals for the columns, multiply those times the frequency totals for the rows, and set that over the sample size. So from our previous example, it would look like this. So uh, we saw that our row total was 50, right? So and our column total is 42. So for this particular box, we're taking 42 times 50 and setting that over 100, right? So that's the calculation up here. The example is here. So that equals 21. And this number here, the romantic and no cell, was found by multiplying 58 times 50 and then setting that over 100. So oops, sorry, our statistic is our test statistic is exactly the same as the previous one. So we're just again taking the difference between the observed frequency and the expected frequency, squaring that, setting that over the expected frequency, and then adding all the values that we get for each category. So the only thing that's different is our degrees of freedom. So that is the row total minus 1, and then however many columns there are minus 1. So you're taking those two values and multiplying them. So that's how we get our degrees of freedom for this particular test. So from our previous example, the whole calculation would be like this. So our observed frequencies, again, that's what we just, what was observed from the actual data. And our expected frequencies based off the null hypothesis and that calculation, the formula. We're just subtracting the values in any given box with the corresponding box in the expected frequencies. So this top left box, we're taking the difference between that and then the top left box here, right? And that's what we're squaring and setting over 21. So you can see that we have the calculations down here. Each term corresponds to the box positions, and we get a final keyscore statistic, and we compare that with our cutoff, and then we see whether we have a significant effect or not. So that's pretty much it for how that test is done. And for all these tests, we also have measures of effect size. So once you calculate your keyscore statistic, you can set that over n, and then multiply that times degrees of freedom asterisk. So what is degrees of freedom asterisk? That is the smaller of either row minus one or column minus one. Okay, so we set all that within the square root. So we take the square root of all that and we get this Kramer's V. And this ends up being our measure of effect size. And of course, we have a table that will tell you what's considered a small, medium, or large effect. And that's how we know whether, if we do find a significant effect, whether that actually has some practical value to it. All right, so that's it for the lecture. Um, I'll put up some practice problems. That'll give you a little, just kind of show you how they're done in practice.